Hello everyone, welcome to our differential equation class. In this video, we introduce first-order systems of nonlinear differential equations, in particular autonomous systems. And for those systems, we are not going to try to find solutions of these equations because they are usually too complicated to find exact formulas for the solutions. Instead, we are going to sketch and approximate phase portrait of the solutions. We are going to sketch and approximate phase portrait of the solution using what is called the linearization analysis, which starts with finding equilibrium solutions and then finding a linear system that approximate the nonlinear system near the equilibrium solutions, and with that information we can sketch and approximate phase portrait of the solutions of the nonlinear system. So that's the plan for today. Let's start introducing first-order systems of nonlinear differential equations. A 2x2 first-order system of nonlinear, but we also include linear differential equations, is a system like this, where we have two equations for two unknowns. The unknowns are the functions x1 and x2, which are functions of the independent variable t, which we also call time, and the time derivatives of these functions are related by functions f1 and f2 to the variable t and x1 and x2. When the functions f1 and f2 are linear functions of x, then we call that the system is a linear system, otherwise the system is nonlinear. The system given here is called autonomous in the case that the functions on the right hand side of the equations do not depend explicitly on the independent variable t. These equations are written in what we call component notations for the components x1 and x2, but we are also going to write a system of equations in vector notation, and in vector notation these equations can be written in this way, where we introduce the vector containing the variables of the system x1 and x2, and on the right hand side we introduce the vector containing the functions f1 and f2 that defines the equations in the system. Notice that given any two components, for example x1 and x2, these two components define a vector and also they define a point. If we do a picture, we see that any two components define a vector on the plane, but also define a point which is the endpoint of that vector. When we write differential equations, we choose to highlight the vector interpretation and the component interpretation in different parts of the equation. So we highlight the vector interpretation here for the derivative and the point interpretation here for the point where this vector is defined, the vector field is defined. This is not very important, but it's just in case you wonder why sometimes the variable has an arrow and sometimes it doesn't. Is that we are thinking the two components as a vector, or we are thinking the two components as the endpoint of that vector. Again, not very important. So let's see examples. And the first example is to show that the systems introduced above include also linear systems, like this, when A is a matrix. So let's see that first. Solution. So let's write down the system from vector notation into component notation, and for that we introduce the component x1 and x2 and the derivatives of these components. The equation says is related to this matrix vector product of this matrix A, B, C, D with the vector components x1 and x2. Okay, let's write it a little bit nicer. And what is that? Well, the matrix vector product, if we recall, is going to be A x1 plus B x2, and here we have C x1 plus D x2. So we have an equality between two vectors, which means both components have to be the same, and here we have the equation for the system. In component notation, x1 prime is a linear combination of x1 and x2, and x2 prime is another linear combination of x1 and x2. Well, but these are the functions f we introduced before, f1 of x1 and x2, and this is the function f2. As you see, linear functions in the variable x. So how does it look like? The field vector function of x, well, is given by this component x1, the first equation, the first right hand side of the equation, and the second right hand side. Oh, here there is a mistake. This should be d, and then here it should be also d x2. So as you see, the vector field in this case for the equation, what we have called f of x, is nothing more than the vector product of the matrix with the variable, in the case that the equation is linear. So linear equations are a particular case of the systems we introduced above. But the systems we introduced above are more general than linear equations because includes other systems like, for example, this one, what we call the competing species system with infinite food resources. What is that? Well, it's a system of equations where the variables x1 and x2 describe the populations of, for example, rabbits and sheep, which are competing for the same food resources, although the food resources are infinite. And here is the system. Let's try to understand a little bit why this system of equation can represent the competition of two populations for the same food resources. To understand that, let's suppose we don't have any sheep. So the population of sheep is 0 and we have only rabbits. If we go to the second equation disappears completely because this is sheep, this has sheep, and this has sheep. So the whole equation disappears. And in the first equation, the second term disappears. And then the rest is only an equation for the rabbits, and you see is the exponential growth equation because we are considering R1 positive. So this is what happens when we have one species having infinite food resources. The population grows exponentially. When we have only sheep and no rabbits, then the first equation is going to disappear completely, and the second term on the second equation disappears, and again we have the exponential growth equation for the sheep, because R2 is again a positive constant, and this is what happens with populations with infinite food. They grow exponentially. So when we have both populations, then we have these two terms, but now the populations are competing for the same food resources, so we add a negative term, again alpha, the birth rates and the interaction coefficient, they are all positive constants. So we introduce negative terms with the product of the two populations, x1 and x2. This product is going to be larger. The larger are the population, which is a way to measure the overlap between the two populations. When the populations overlap, they are competing for the same food. So when they overlap, the rabbits cannot eat all the food they want, so that decreases the rate of change in time. And the same for the sheep, with different coefficients. So this is a simple model that describes two species competing for the same food, and the food are infinite. infinite resources of food. This is an autonomous system because all these coefficients are constants. We don't have t explicitly in the equation, only through the variables, so this is an autonomous system. Notice that this system is coupled in the sense that we cannot solve for x1 because it contains x2, and we cannot solve for x2 because that equation contains x1. And also is nonlinear because of this term. This part is linear, but this part is nonlinear because we have a product of the two populations. So this is a coupled nonlinear system. The system, which is written in components up there, can be written, of course, in vector notation as follows. We introduce the... So it's going to look like this. X is going to be equal f is a vector, which is a function of the variable x. And the vector here, the vector field, is something like this, the right-hand side of the components, which is, in this case, r1, x1, minus alpha 1, the product of the two populations, and then r2, x2, minus another coefficient, the product of the two populations. So this is how the vector field looks like for the competing species system with infinite food resources. There are a particular type of solutions to nonlinear autonomous systems which are simple to compute, and these are called equilibrium solutions. Equilibrium solutions are constant, that means time-independent, solutions of a first-order system of differential equations. Equilibrium solutions are also called critical points, and in components, if we use the notation of a point for x1 and x2 and a 0 for equilibrium solution or critical point, this point is going to be a critical point of this system of equations if and only if, well, is a constant, time-independent solution of the equation. Because it's constant, these time derivatives have to be 0, and then we end up with these equations for the critical point. These are the equations in components, and in vector notation, well, this system can be written then in vector notation in this way, and then x0 is going to be a critical point if it's a constant solution of this system. So here we have the vector 0, and we have then this equation for the critical point. So here we see a nice geometrical interpretation of the critical point. Critical points are the points where the vector field that defines the equation vanishes. Okay, let's see how these critical points looks like in the example of the competing species with infinite food. And to fix ideas, let's put some particular names for the constants. So let's write, for example, the constant r1 to be 2, r2 to be 3, and so on for the alphas. So we have a particular type of competing species system. Let's find the equilibrium solution of that system. So, solution. Well, let's start writing the system in any form. For example, in vector form, x of t. Here is then a vector field on the solution x of t. And what is the vector field in this case? Well, the vector field is defined, f of x is the vector field with component 2 x1 minus 5 x1 x2, and then the other component is then the second equation, the right hand side, 3 x2 minus 7 x1 times x2. So this is our vector field, And now we are looking for the points, so we need to find the point x, which we call x0, but now we are not going to call it x0 right now, so to avoid writing so many, we are not going to write it like this because we need to write a lot of zeros. So x, which is x1 and x2, solution of the equation, well, the vector field at this x1, x2 vanishes. Okay, so then the equations we need to solve are x1, common factor of 2 minus 5 x2 has to be 0, and x2, common factor of 3 minus 7x1 has to be 0. So this is the system of equations we need to solve, and here is one solution. It's a very simple solution. When x1 is 0 and x2 is 0. If x1 is 0, we satisfy this equation. If x2 is 0, we satisfy the other equation. So here we have one solution. So one critical point, for example, is the critical point x0, which is the point 0, 0. Very well. So what happens if we look for solutions with x1 equals 0 now? If x1 is 0, but x2 can be different from 0, so if we put x1 equals 0, then we satisfy the first equation, and then this is 0 here, and notice that now x2 has to be 0 in order to be an equilibrium solution. So if x1 is 0, then x2 has to be 0, and vice versa. If x2 is 0, then x1 has to be 0. So the only other possibility is when both are different from 0. If x1 is different from 0 and x2 is different from 0, then these two factors have to be 0. So we have two equations. The first equation is 2 minus 5 x2 is 0, and the other equation is 3 minus 7x1 equals 0. From here we get that x2 has to be 2/5, and from here we get that x1 has to be 3/7. And then we got another equilibrium solution or critical point, the point x1, which is 3/7, 2/5. And these are all the equilibrium solutions for this system. So we can draw these solutions in the plane x1, x2, and here is the result. So the solution, the equilibrium solution 0, 0, and the equilibrium solution x1 somewhere here at the point 2. Actually, this is incorrect. 2/5, 3/7. There it is. 2/5, 3/7. So this is how equilibrium solution looks like. So it's a point constant in time that solves the differential equation. So this is how we compute equilibrium solutions of a nonlinear system like this one here. What about computing all the solutions of this system? When the system is nonlinear, there are in general no formulas for the solutions, general solutions of nonlinear systems. And what we can do is we try to find out qualitative properties of the solutions of nonlinear systems without computing exact formulas for these solutions. equilibrium solutions are going to play an important role in how we obtain qualitative or approximate solutions. And the method we are going to use to obtain this information about the solutions, the qualitative or rough idea of how the solutions behave, is called the linearization method. And here we are going to describe the main idea behind the linearization method. So consider a nonlinear system of first order differential equation given by this equation, and suppose we have x0 to be any point on the plane x1, x2, any point here, equilibrium solution or not. What we can always do is we can always compute the Taylor expansion of the right-hand side of the equation. Recall the right-hand side of the equation is a function of two variables. And we can always compute the Taylor expansion at around any point on the plane x1, x2. So here is the Taylor expansion. The Taylor expansion of a function of two variables is the function evaluated at the point where we are centering the expansion, then the first derivative of the function evaluated at that point, times the difference between any point and the point we are centering the expansion, and then the remainder. The remainder is usually small when x is close to x0. Okay, now assume that the point you are centering the expansion is actually a critical point, which means the function, the field evaluated at that point vanishes, as we saw before. So this term is not there. Okay, so here it is. So with that, when this term is not there, the equation, the differential equation, looks like this. The only thing we have done is we have written instead of f the expansion, and we have used the fact that the point we are centering the expansion is a critical point, so this is 0. So this is how f looks like in that case. Okay, so now let's recall that this is a fixed point, so it's time independent. So the derivative with respect to time is 0, so we can replace this this function by this function here. So now the equation looks like a little bit nicer if we introduce the variable delta x, which is the difference between the point and where the point, an arbitrary point or an arbitrary solution of the equation, and the point we are centering the Taylor expansion. And then the differential equation in this new notation looks like this, where here we have the difference between the solution and the point and the equilibrium solution. This is the difference from a solution and an equilibrium solution. The difference appears again here, and this function here depends on the difference. And what is m? M is this object here that contains all the derivatives of the function f, and this is actually a 2 by 2 matrix that we are going to compute pretty soon in a few examples. So, but it's a constant matrix. So after doing all this calculation, we see that the nonlinear equation can be written in this way now. And this way is very nice because what it's saying is that the nonlinear equation can be written close to an equilibrium solution, can be written as a linear system plus a remainder. That the remainder here is close to 0 when we are close to an equilibrium solution. Okay, so now here is our main statement, and the main statement is that from this calculation is that if the remainder is small for x close to equilibrium solutions, so delta x small, then close to equilibrium solutions or critical points, the equation coefficients of the nonlinear system are very close, so this is going to be close to 0. So the nonlinear equation coefficients are very close to a linear system with this matrix. This matrix, recall, has the derivatives of the field. So what we are saying here with this little analysis is that the nonlinear equation behaves like a linear equation when the solution is close to an equilibrium solution. So now the main question is, okay, the equation coefficients look very close to a linear equation. So what happened with the solutions? And what people have proven is that in many cases, the solution of the nonlinear system are also close to the solutions U of the linear equation. So this is the idea we are going to use to obtain the qualitative properties of solutions of nonlinear systems. We are going to see how these solutions behave close to equilibrium solutions, and to do that we are going to solve this linear system that we know how to solve, and the behavior of the solution of the linear system is going to tell us how the solution of the nonlinear system behave close to equilibrium solution. And with that we are going to be able to understand the behavior of the solution of nonlinear systems. Before we continue, let me fix a couple of things. The function g in the remainder is a vector value function, so I should have arrows here. Okay. So what we did here is we mentioned what is the idea to find qualitative behavior of solution of nonlinear system by computing these linearizations. Okay, so now let's write down a summary of what are the calculations we need to do step by step in this linearization analysis. Recall, the linearization analysis is to try to find qualitative behavior of solution of a nonlinear system. So we need to start with a nonlinear system, and then we are not going to try to find solutions formulas, because in general these are too complicated and we don't know how to find solution formulas for nonlinear systems. Instead, what we are going to do is we are going to sketch an approximate phase portrait of the solutions. That's all we are going to try to do. And we do it with this idea called the linearization method. This idea works for autonomous systems only, so systems of this form. And here the vector field f is going to have component f1 and f2. What is the first thing we need to do? What we did before. The first thing is to find the equilibrium solutions x0, which are the constant solutions of the equation. So these are the points where the vector field vanishes. That's what they are called sometimes critical points. The next step is going to be, in this linearization method, to find what is called the derivative matrix, also called the Jacobian, which is the matrix that we were mentioning up here, over here. What we're going to need is the matrix evaluated at critical points, but we go over that in a minute. First, we need to compute this matrix that contains all the derivatives of the vector field, and there are two functions and two variables, so there are 4 derivatives, and here they are. In the first row, we have the derivative of the function f1. On the second row, we have the derivative of the function f2. You see f2, f1. In the first column, we have derivative with respect to x1, x1, and x1, and here derivative with respect to x2. So we construct this matrix that is a function of x, is not constant. This matrix right now is not constant. is gonna be a constant matrix when we evaluate that matrix at each critical point. In our previous example, we had 2 critical points, so we are going to have 2 of these matrices, which are going to be constant matrices, which are going to be the derivative matrix evaluated at each of the critical points. With each constant matrix, we can then solve a linear system of equations that has this constant matrix as the coefficient matrix of the system, and then we obtain the solution. So U is going to be the solution of a linear system with coefficient matrix given by the derivative matrix evaluated at the critical points for each equilibrium solution x0. What we are going to do next is we are going to study these solutions of linear system. Solution of linear system we know how to compute, so we can study those solutions, and we are going to use the eigenvalues and eigenvector of the coefficient matrix, which is the Jacobian evaluated at critical points. We are going to use the eigenvalues of this matrix to characterize the solution of the linear system near the solution of this linear system. And by characterize, we mean we want to know if these solutions behave like sources, node or spirals, sinks, node or spirals, saddles, nodes, or centers. We want to see how the solution behaves. These are all the possibilities that we have seen this type of solutions in a previous video. So we know the solutions of linear system behaves like one of all these possibilities. And then once we know that, we are going to relate the behavior of the solution of the linear system with the behavior of the solution of the nonlinear system. And this relation, well, there are many theorems that relate these two solutions, the solution of the nonlinear system near equilibrium solutions with the solution of the linear system. And the theorem we are going to use is called the Hartman-Grobman theorem, that says that the behavior of these two solutions, nonlinear and linear, is the same near equilibrium solutions for all cases: sources, spirals or nodes, sinks, spiral or nodes, saddles. So for all these cases, the behavior of these two solutions is the same, and the only case that it could be different is for centers. So, except possible for centers, the behavior of these two solutions are the same. With that information, we are going to be able, so with all that information and a little bit more, we are going to need to compute the direction fields of the nonlinear equation. With these two pieces of information, we are going to be able to sketch the phase portrait of solutions of nonlinear systems. So that is, in one page, the linearization method. And now we are going to use it in a particular example. The example is the competing species with infinite food that we introduced before. The first step, recall, is to find the equilibrium solutions, but we already did it. They are up here. So 0, 0, and this point are the equilibrium solutions. We have two equilibrium solutions for the competing species. And now the next step is, in the linearization method, is to find the derivative matrix. So let's do that. Solution. The derivative matrix, recall that we have two equations. The equations are x1 prime is equal to some function of x1 and x2, and x2 prime is some other function, which we know the functions, they are right here. Function of x1, x2, and with that we compute the field. The field of the equation is, well, f1 and f2, and here is and the function f1 and f2, of course, are f1 is nothing more than 2x1 minus 5x1 x2, and of course f2 is 3x2 minus 7x1 x2. These are the fields. Maybe if we can write it down here, it's gonna be a little bit nicer. Okay. So what do we need to do now with all this definition? Recall how we construct the derivative matrix, which in general is a function of x. It's not constant in general. And what is that? Well, in the first row, recall we need to compute f1 and f1, then f2 and f2, and in the first column we need to compute derivatives with respect to x1, and in the second column derivative with respect to x2. So this is how the derivative matrix looks like. Okay, and now let's do these derivatives. Well, first let's write down what these derivatives are. Derivative with respect to x1 of f1, but f1 is 2x1 minus 5x1 x2. Then we have the derivative with respect to x2 of the same thing, 2x1 minus 5x1 x2, and then we have the derivative with respect to x1 of the second component of the equation, so it's 3x1 minus 7x1 x2, and then the derivative with respect to the second variable of 3x2 minus 7x1 x2. So now we need to remember that computing the partial derivative means derivative with respect to that variable, keeping the other variable constant. And if we do that, we obtain that here the derivative, we derivate that, and x2 is a constant in this derivative, so we are going to obtain 2 minus 5x2. Then here we are going to obtain derivative with respect to x2, so this is 0, and with respect to x2 we obtain that, so we obtain negative 5x1. Down here we are going to obtain 0 and then negative 7x2, and here is going to be 3 minus 7x1. And you see this is the derivative matrix, which is not constant, is a function of the point x. Okay, we got the derivative matrix. What is next? Next is find the linearization, so the derivative matrix at each critical point, and solve the linear system. Characterize these linearizations. Okay, so the first thing we need is the derivative matrix, so we are going to copy this result, copy over here. And actually what we need is, we are going to emphasize that this is a function of the point, so we are going to put here x1, x2. x1, x2. So we are finding the linearizations. Okay, so the first thing we need to do is evaluate this derivative matrix at 0, 0. So let's do that. So let's do it maybe here, the derivative matrix at 0, 0. You see x1 and x2 are both 0, so that disappears, that disappears, that disappears, and that disappears. So we get the matrix 2, 3. It's very simple matrix, a constant coefficient matrix, 2, 0, 0, 3. This is the matrix M we mentioned before. Well, we know from this matrix, just by looking at this matrix, that it has the eigenvalue lambda plus to be 3 and lambda minus 2, and the eigenvector v plus, the corresponding to lambda equal 3, is actually the vector 0, 1, and here the v minus the smaller eigenvector, the eigenvector corresponding to the smaller eigenvalue is actually the 1, 0. So here we have, so now what we need to do is we need to study the solution of the linear system, to study the solutions of the linear system, and here is the linear system u prime equal to 0, 0, 3 acting on u. And this linear system with these eigenvalues and eigenvectors has the following behavior. We have the vector v plus that points in the direction 0, 1, so up there, the vector v minus in the direction 1, 0, and then we have a source node behavior for the solution of this system. So now let's move on to the next critical point. So now we need to compute the solution. Let's do it here, the derivative matrix at the other critical point, which was 3/7 to 5. And at that critical point, we need to evaluate the matrix of coefficient that we have up there. So let's copy that. It's going to be 2 minus x2, and x2 5 times x2, which is 2 over 5. Then we have minus 5 x1, but x1 is 3/7, and then we have minus 7 x2, which is 2/5. This here is a 5, by the way. And then 3 minus 7 multiplied by 3/7. Alright, this is our derivative matrix, but notice that here the 5 cancel out and then the 2's, so this is a 0. Over here we have a 15/7, here we have minus 14/5, and here again 0. So a coefficient matrix like that. If we compute the eigenvalues of that matrix, we can try to what we need to do is we need to solve 0 equal the matrix that is minus lambda negative 15/7 minus 14/5 minus lambda, the determinant of this matrix, which is nothing more than lambda squared minus, we are going to have 15/7, the negative signs cancel out, and then 14/5, but this is nothing more than x squared. We have a 3 out there and a 2, minus 6. So the characteristic equation is simply lambda squared minus 6 equals 0. So we have eigenvalues lambda plus, which is going to be square root of 6, lambda minus, which is negative square root of 6. So one positive, one negative, so we have a saddle node. For the behavior of the solution of this linear system. And now we should compute the eigenvalues, well, the eigenvectors, sorry, but we are going to leave it as an exercise, and you're going to see that if you compute the eigenvector corresponding to lambda plus, you're going to get this number, this vector. If you compute the eigenvectors of lambda minus, you're gonna get this vector here. So one same components, just one has a negative sign, one has a positive sign. And what we can do right now, if we can verify that this strange vector is actually an eigenvector. For example, let's verify that. Oops, let's verify. Why not? So we have 0, our metric is 0, negative 15/7, and then negative 14/5, 0. And we want to act, this is our matrix of coefficients, and we have our vector here that is the vector with component negative 15/7 and square root of 6. And recall, this is our derivative matrix, so the matrix of coefficient df at x1. This here is what we are calling our eigenvector v plus, and let's see what we get when we do the product. We are verifying that this is actually an eigenvector because we do the product, and we are going to get negative 15/7 times square root of 6. And down here we are going to get negative 14/5 multiplied by negative 15/7. Very strange number, but see what happens. We have on the top, we don't do anything, square root of 6. On the bottom, well, we have the same cancellation as before, and we have a 6. So we can pull common factor a square root of 6. And what do we get? We get the vector negative 15/7 and square root of 6, which happens to be v plus, and that here is what we call lambda plus. So yeah, this is an eigenvector, and check that the other is also an eigenvector for the other eigenvalue. So now we need to study the solution. So study the solutions of the linear system u prime equal, now we have this coefficient matrix 0, negative 15/7, negative 14/5, 0, but we have the eigenvalues and eigenvectors. So with that we have the phase portrait, and as we said before, this is a saddle node where, recall, this eigenvector has two positive components, so points in this direction. This is the v minus. This one has a negative component horizontal, so this has to be the v plus. So this is the v plus, this is the v minus, and this is how the phase portrait looks like. Okay, so now we have the behavior of the solution of the linear system. One behaves like a saddle, the other behaves like a source. Now what? Well, now we have the main theorem, the Hartman-Grobman theorem, that says that the behavior of the solution of the nonlinear system near this critical point and that critical point behave in the same way as the solution of the linearizations, which the linearization is a source and a saddle. And the solution of this linear system, what that means is that this linear system, this is how the solution of the nonlinear system behave around those critical points. Recall, the critical points were 0, 0. This is for the nonlinear system, and the other was somewhere here, isn't it? Well, the behavior of the solution of the nonlinear system behave like a saddle, and here they behave like a source. This is for the nonlinear system now, thanks to the theorem. that translate the behavior of the linear system into the nonlinear system, and this can be done because this is a source node and this is a saddle node. If we had a center, we need to do some extra work. Here we also need to do some extra work because now we want to see what is the solution, the behavior of the solution around here, far away from the equilibrium solutions. And for that, we need to do a little bit more study. So let's start with the nonlinear system. Recall this is our nonlinear system. And what we need to do is we need to study the vector field associated to that system, which is, of course, 2x1 minus 5x1 x2, and here we have 3x2 minus 7 x1 x2. So this field, we are going to evaluate this field on two places, on the points of the form x1 0. So we are going to make x2 equals 0, so that disappears, and we get 2x1 0. Notice that this is a horizontal field, so a horizontal vector. And now the vector field at 0 x2. Well, this is going to be 0 3x2. Well, these are a vector field that is a vertical vector field pointing up. So if we put that information into our picture, so if we put the vector field on in the case when x2 is 0, x2 is 0, so here the vector field is horizontal, so this vector field is this vector field here. So this is the direction field. I don't know how long is the vector, I'm normalizing. And then when x1 is 0, so along this axis, the vector field points up, like here. Okay, this information about the vector field and this information about the behavior of the solution of the nonlinear system near these critical points, and the fact that the solution curves are always tangent to the direction field, is enough for us to understand what is going to be the behavior of the solution everywhere else. And here it is. So recall, solution curves do not cross direction fields, and then this is what we get. So here we have our center, our saddle. Here we have a source. I'm plotting only in this region because for population we are interested only on positive or zero populations. And this is how the behavior of the solution. Here the solution has to stay on the line. The solution has to stay on the line because of the vector field. And then we have a saddle here and a source there, and this has to be the behavior of the solutions. Notice something kind of interesting about this, the behavior. We haven't solved the equation exactly, but we know how all the solutions are going to behave. Notice that this system, which is a population model with infinite food resources, always predicts, well, not always, but in most cases predicts, this model predicts that one of the species is going to go extinct. Because suppose you have initial data here, what is going to happen is one population x2 is going to grow to infinity, but the other population, you see, x1 goes to 0. If the initial data is here, the opposite happens. We are going to go like this. Population x1 goes to infinity, population x2 goes to 0. So this model predicts, according where the initial data is, there is a line here that separates the behavior. So we have two different behaviors. The behavior for initial data on this region. On this region, if you put initial data whatever you like for the two populations, but on that region, then here x2 survives. And if you put initial data on this region, whatever you like on that region, it goes to infinity, but we are not gonna draw it to infinity, obviously. But if you give initial data on any point on this side of this curve, then here x1 survives. And that's it. This is how we can find the behavior of solution of nonlinear system without solving exactly the nonlinear system, instead by studying the direction field in some places and by finding the behavior of the solution of the nonlinear system around equilibrium solutions. That's it for today. See you guys in the next video.